So, thank you for joining us this evening to hear about the work of CED. It does give us great encouragement when others come and hear about our work. Whether you are a CED member or you're just joining us for this evening, you're very welcome. My name is Angus Armstrong, and I'm organising the Tech Talks this season. We have a programme running through to April next year. They're all at they're all at 7 o'clock on Thursday nights, and they're around this point in the month. So keep an eye open. We do an email shot to folks, and we also publicise it through our Facebook page. Tonight's talk is by Nigel Healer, the owner of WaterReach, which is our not-for-profit company, which Nigel has developed through the latter part of his employed years, and now runs it in his retirement. Nigel used to work for Thames Water and is drawing on all of that experience to make WaterReach work. So tonight, Nigel will be telling us about the Clariwash filtration system, which I've been hugely enthusiastic about since the first time I kind of heard about it. And he is the inventor and developer of that system. So thank you very much, Nigel. And to everyone who's participating tonight, all of our Tech Talks are available on CED's website and on our YouTube channel. And this one should be available sometime tomorrow. So without further ado, I'll hand over to you, Nigel. If you can run your presentation and maximize yourself on the screen. Or if you share, once you've got your presentation running, if you share your screen, that should...
Is that visible to everyone? I hope you can still hear me.
Yes, what I'm going to do is switch off the participants. Yeah, we're all muted. Great, go for it.
Okay, thanks Angus, and thank you to CED. I should mention actually that I'm very much a member of CED, as well as the WaterReach thing was really just to be able to go out wider, but I'm still very much a member of CED, and they have obviously participated in the development of this. And I know Angus has given some generous words about it, but it's very much a pulling together of ideas that all sort of already existed in a way, and research that had been done by others, and making use of that really in the development of the system. It is I think regarded as a faith-based operation to see how far this thing runs and how far God wants it to go really, and it goes so far or it keeps going. We'll have to see really. So just to say that, and the name Clariwash, just to say, is just a name to identify this as a system as distinct from any other system really. It's a name you may like or loathe, but it's there at the moment. So so that's it really. So just to get a bit of history, I first thought of this actually and saw the idea of backwashing a filter with a siphon is an existing idea that's been in use in the industrial water area of water treatment for many years. And I became aware of this idea and thought that actually looks quite a good idea for the developed world. But the systems that they had were very large. You'd had a sort of 8 to 10 meter sized tank with multiple compartments. So you'd have horizontal bulkheads in the tank, which would have raw water above, a filter in one section, and then treating water and a backwash tank at the bottom section, all of which look very difficult to do in the developing countries to actually achieve the quality control where you might have any leakage between treated water and raw water. You could potentially get contamination. The siphon was enormous, so you had to have a small siphon to prime the large siphon. And so this idea was, the benefit of that is you can put the tank down anywhere and you've basically got the whole system in one. But for us, where we were looking, it was going to be much smaller for the developed world communities. So my thought was, can we just break it up? And instead of having the backwash tank as part of this huge tank, use a cheap as chips plastic tank you can buy in Kampala. And could we just use pipe filters initially and break it up so that basically you produce individual units to create more flexibility. And so it was really developing that idea and the hydraulics around it to make it work reliably. And the idea also allowed us and lent to the introduction of a clarifier upstream of the filter, which has, I think, greatly enhanced the design, really. And that's a development that's sort of taken place as we've gone, really. So that's just by way of introduction. So I initially thought, well, when is this going to start? I thought, well, there's a point in time where I thought, well, let's build something on my workbench at home. I took that along to a CED meeting, AGM, and then in our London group, someone said, oh, someone who's a lecturer at South Bank University gave us the opportunity to build a test rig at the university without any charge, actually, which was amazing. And so we were able to create a much larger test rig to check the hydraulics out on that. And then Dick Holloway, who is the director of CED and has passed away perhaps about 2 years ago, said, why don't we use this in a big scheme called Kisakagana in Uganda as part of that scheme on the most turbid part of the scheme. And so that was an opportunity then to deploy it into the developing world. And that's really where it started. So so this really is the concept, the Clariwash self-washing filtration system, a new concept in water treatment for communities. And I should say that this is not a household point of use type system. It's not a small community system. It's probably 150 upwards to thousands of people. That sort of size really is what this is for. This one shows the larger size, actually, this diagram on this slide. So this is basically the system as we have developed it as a pipe system. I thought I would just briefly talk through this, the way it works very briefly, but as a separate part of the presentation. There is a more detailed part, which if people want, we can go into at the end, if they want more detail on how it actually operates. But basically the flow, you can see here, we've got the inlet pipe, the clarifier, the filter and the backwash tank, all as pipes with plumbing and relatively cheap to make and get the hold of the equipment, basically. Raw water enters the inlet pipe. It's aerated at the top here with a simple cascade, or you could do a more vigorous eduction of air if you wish, if you needed it. The flow goes down through this pipe. This basically has a fluctuating level and allows a buildup of water in here, which is used to prime the siphon. The water flows down through the inlet pipe, up through the tube clarifier. That I don't know, for those of you who aren't familiar with the details of water treatment. If you've got turbid flow, which is not turbid, another word where it's a lot of movement within the water will stir up turbulent flow, will stir up the sediment and prevent it from settling. And you'll see that in a stream. If you've got a turbulent flow in a stream, you can see all the mud being churned up. And then the idea of the tubes here is that there was still flow, so that the streamlines are parallel and the settlement velocities of the particle within that flow increases. And so the idea of the tubes is that as the water passes up through here, it's turbulent at the bottom, and then it becomes slowly through a transition zone in lamellar flow where it's tranquil, and the settled particles will then form a cloud, which then intercept more particles that come up into this cloud and gradually build up in this settler until such time as they move across to the filter, at which time it blocks the filter and initiates the backwash. So that's the tube clarifier. It then passes across to the filter and down through the filter media. For the filter media, we're using a high quality filter media. And at the Mapanga Gorge installation, we've actually also added a second layer of coarse media to the top of that, making it a dual media filter. And that coarse layer is really to prevent the blinding of the layer below where there's fine material. So the flow is then purified with the filter. It passes then across to the backwash tank. And from there, it goes into supply. Chlorination is applied either into the backwash tank or downstream as it enters another tank, which would be your supply tank, which would feed your tap stands downstream and would be able to store water for diurnal variations. So that's basically forward flow. For backwash, basically as the filter clogs up, as particles fill the pores within the media, the resistance builds up to the flow through the media. And as that builds up, you need an increased driving head to drive that flow through the media. And that's provided by the level of water in the inlet pipe, which gradually rises to the top water level that it can go to by the system. That is balanced by the U-tube system, which has acts like a manometer really, and it's got a differential head. When it reaches the maximum, the air is pushed around the bottom of the U-tube, which activates the U-tube, and then there's no resistance, and all the water in the inlet pipe is able to move quickly downwards, up through the tube clarifier, over the siphon to waste, and that basically both flushes out the tube clarifier of its sediment, but also acts to prime the siphon. Once the siphon is primed, it then draws down this level in the inlet pipe rapidly to the base here. That causes a reversal of pressure from positive to negative in the top of the filter, and that basically reverses flow through the filter, and the water in the backwash tank is drawn into backwash the filter in reverse. That backwash will continue maybe 5 minutes or so, and as that proceeds, the water level drops in the backwash tank to below the air pipe, and that then allows atmospheric pressure to enter the top of the filter and break the siphon. So that's basically how it operates the cycle. Once the siphon is broken, the levels just stabilize, and there's a sort of warm-up period where the whole system refills with water. And that's quite important because you often get turbidity coming out after a backwash. You tend to get back some turbidity coming through, and it's good then to have a slow start to the filter run or a delayed start. So this gives you the delayed start really. So that's basically a very quick outline of how the system operates. As I say, we can do more detail on that with a series of sequence slides if this time or not, as the case may be. So the advantage here are listed here. It's suitable for long-term use in improving water quality for communities in developing countries. So that the ones in Kisiki-Ghana have now been operating for about 5 years, in Mapanga Gorge, getting on for 3 years, I think now. And there's very little operator intervention to keep them operating. It's hydraulically automatic, so there's no control system, there's no power supply. You don't need an operator to go and switch a load of valves to do the backwash. So if it clogs up in the middle of the night or in the early hours of the morning, or Christmas Day or something, it'll backwash it itself. You don't need to send someone out there to go and do the backwashing. No moving parts, no need for replacement parts. There's a multi-barrier approach to purification of the water. So if one barrier fails, if you lose your disinfection, for instance, you've still got aeration, clarification, dual media filtration there as well anyway. So you're not totally reliant on one barrier. High grade filter media, AFM grade 0 from Dryden Aqua, is used as a filtration barrier. That's the fine media. And where possible, the use of treatment chemicals such as coagulants is either eliminated or minimized really. We do rely on chlorination, but not hopefully unless the water really requires it, using coagulants. And the self-washing system utilizes established hydraulic principles to periodically self-wash the system, such that both the clarifier and the filter are cleaned in the one cycle. So that's really the advantages of the system. Looking at the current formats and locations that we have, just looking at the sizes here, the university rig was a 200mm pipe filter, gradually going up slowly in sizes. The Kisiki-Ghana one, we upped it to 250, but it's really a question of scaling effects. If you change the sizing, then the hydraulics are subject to scaling effects. And I was very nervous about going beyond what had been tested really. So we went slightly up for the Kisugagana one. Then we went to, we had actually proven on Kisugagana that a larger siphon would prime. So we were able to go to a 300 pipe filter at Mapanga Gorge. And then there's a potential modular version, which is a 300 square version, which hasn't yet been produced to date, but could be suitable for mass production. And I'll show you a picture of that one. And then a sudden step up to 850 square clarifier and filter. And this came about really from a water company in the Philippines, a place called Camarines Sur, said that they'd read something about the system, and they said, we've got a population of 30,000. We're supplying them with a water that gets very turbid in the winter and in inclement weather. And we have to shut off the supply. We're chlorinating it, but when the turbidity goes too high, we just basically have to shut off the supply altogether. Could we do one of these systems for that? So it's a bit of panic mode. Could we actually design this without any real testing of this at that scale? And would it work, just based on theoretical considerations? And so that they basically built this at their own cost out there. And we've done they have done testing of a simulation of the backwash, which seems to be quite promising, actually. So it's still a bit under trial, but it's early promise. And on that basis, we're going to use the same design for supplying to Kagando Hospital in Uganda. So that's really the sizes we've done to date. Could go bigger, other sizes could go much bigger, but the other limit that I was trying to achieve was to make this lightweight enough to be able to not need craneage. So you could, deliver this on a lorry and you get 4 or 5 guys to manhandle it off a lorry, take it up a hillside off road, not need crane access. And that was quite important. If you go much bigger, you're going to probably have to go to steel. That would become heavier, and then you're into the sort of the low end of municipal engineering, and that wasn't somewhere where at the moment I felt that I could go. So that's really where it stands at the moment. This basically is a drawing of the modular version. So here, if you look on the right, you've got the components. Really, this is a formed clarifier filter unit in square section. Each one is a square section, but it's a single unit. And the pipes, the clarifier pipes just drop inside this, and you have a lid that drops down. The media goes in the other side, and you have a lid that drops down on top. And then this is the inlet pipe is just a 300 pipe, and the U-tube housing is 300 pipe and a tank. And if there was a program where we wanted to deploy this filtration system on a wider scale, in a large number of villages, say, and there was a program to do this, this could be mass produced to do that, and it would be easier and quicker to deploy. So it's a concept at the moment, but it could be, it uses the same hydraulics really as the 300 pipe size. So there's a reasonable degree of confidence in it. So that's really where that sits at the moment. So I just thought now I'd go through a little bit of the details of installing these in these sites. So the first one at Kisugagana can be seen here. You're carrying up the units up the hillside, quite an arduous climb up there. And you can see that they've been made by the factory in Uganda to a certain degree. They've built them to the drawing specs, but the quality of that was quite suspect. They were glued together, and some of them came apart very easily. And we spent many happy hours sorting out leaks from the tops of the filters, and there's a certain degree of complexity in this lot. So it was done. We did probably put 5 filters in about a week, but it was quite detail intense work. And so the effort from there and the learning was really, can we simplify that, make it easier to deploy, really? The Kisugagana one doesn't have the clarifier. The clarifier, if you look at this pipe, I hope you could see the arrow moving up and down this pipe. That basically, in the subsequent design, became the clarifier, because when you looked at the backwash from these filters, it was obvious there was settlement in these vertical tubes, because you've got that coming out early before the filter was backwashing. And so I just thought, well, why don't we use that and make that settlement zone much more purposeful and actually take out as much sediments as we can early before the filter. And so that's the development from that, really, that moved into the next stage, really. The order of the actual arrangement of the backwash tank in relation to the filters is a bit different in this the diagram, just to fit in the building, really. And this is really the filter building on the top here, and the filtered water tank here. And this is the installation of the filters, and you can see here there's indication of trying to seal the joints and such like that we had to do there. So that really was that scheme. I'm now sort of going in slightly wider field now, because to do that, to bring it back down then to the water, to the Clariwash as we go through this, really, because this Mapanga Gorge installation was actually originated as a part of a sustainability effort for Mapanga River restoration, really. And they were basically trying to work along this river, which runs from a mountain range in Western Uganda called the Rwenzori mountain range, through a place called Fort Portal, Kamwengi, and then out into Lake George. Those places probably may not mean anything, but it's quite a long distance of many kilometers of river. And the charity that was doing this was called Protos. It was a Belgian charity, and they were working with a local charity called Jesse, which is Joint Effort for Save the Environment, to clean up the river. And the principle was, if the river's clean, the health of the people is improved. And this was what we did for our church, actually, the River of Life, seeing our lives dependent on water, both the spiritual water, but also the physical water. Caring for others is part of our role as Christians, really, and creatively finding new ways of dealing with the climate emergency. And this is a quote I have from attributed to Francis of Assisi: start by doing what's necessary, then do what is possible. Suddenly you're doing the impossible. So this is a picture of Mapanga Gorge in West Uganda. Beautiful gorge where the river's cut out this shape through this area, and then it enters the river via a sort of waterfall. And in this area there was a plant called a cycad plant, which I'm not a botanist and I've not heard of it before, and there's a complex Latin name there for this particular plant, but it's the only place in the world where it grows in the wild, in this 5 square kilometer area. You can see the plants here. They look a bit like ferns, actually. I wouldn't have known they were rare, but apparently the dinosaurs used to eat these, so rumor has it. And the program was, as it came to this part of it, was to actually try to save these species. So there was another charity called Save Our Species involved. And so what they were doing was, they had a nursery shown here with young cycad plants, which were being planted out into this area. But because of the slash and burn agricultural techniques and the fact that the villagers brought cattle down into the water to drink the water, they trampled on all these plants that were being planted. So basically it was self-defeating, really. So they came up, this is before we got there, actually, with the idea of putting a ram pump in, a ram pump being a pump that works on the hydraulic energy in the water. And this is Protos putting this in. You can see it's quite an installation. I think it's the biggest ram pump in Uganda. And this pumps up to the top of the gorge, which is about 135 meters higher than the river level. But the emphasis here is no CO2 emissions. This needs no power supply to run the pump. And then at the top of the gorge, you then have the water troughs for the cattle. So you don't need to take the cattle down into the river, to drink from the river, and you have water supply to the villages. So basically the cycad plants are protected, and the villagers don't need to have that arduous journey to fill up their water cans at the bottom. However, when they tested the water quality, they found E. coli and coliforms in the water. And so they were then saying, what could we use that fits in with the hydraulic nature of this whole project that could work? And that's really where we came in with the Clariwash system, because this could be used to work in sympathy with the ram pump. And so the ram pump was diverted into the inlet pipe, and the tube clarifier and filter were installed inside the filter house. as per our diagram, really. And so you can see the pictures of the installation here. And this is inside, looking back on the inlet pipe, the clarifier, the filter. This is the siphon pipe, and this is the siphon pipe coming into the U-tube housing. And a backwash, you could see the turbidity in that backwash flow. And we found on this that the majority of the turbidity was taken out on the clarifier, and the filter seemed to be performing a more of a polishing function. And then this is the Clawman inline sanitizer. This has little chlorine cartridges that you've put into the unit, and you can adjust the dose by the screw top here, which has got a gauge on the side to adjust your chlorine dose. And these need to be replaced every so often. I've been trying to find out how often they do that, and without success at the moment, but it does depend on the chlorine demand, and which with the filtration, it should reduce chlorine demand. So basically it should be possible to reduce the consumption of chlorine. So this is the scheme, really. It was a win for people, a win for cows, and a huge win for cycads. That was the motto, really, of the. And these were the partners: Protos, which is Joint for Water Protos, Joint Effort to Save the Environment, Jesse, Save Our Species. Gained were the delivery partner I was working with out in Uganda and Waterreach. So, yeah, just to give a bit of history behind that scheme, really. So really, that was Mapanga Gorge. Now moving on to the Philippines. I hope people are still don't need to have a glass of water or something at this stage. But this is the Cameron Sur project at the Philippines. Now this is the supply. This is basically the water source, which is up in the hillside, some sort of cave system, and they've got basically a weir across this river coming from the cave and an outlet pipe from that weir. And this is where they get the turbidity coming in when they get inclement weather. And so this is where they wanted us to, could we design the filtration system? They're chlorinating it anyway, but they want to make sure that the turbidity is low enough to make sure that it doesn't rise above 100 NTU, which is where they shut off the water supply, really. So this is really the design of the larger system. So you can see here you've got a much larger inlet pipe. It's 600 diameter. The clarifier and the filter are made from the same mold, so it's fiberglass, so that basically you just have the same mold for both for economy, really. But the lids are different, and the internal fitting out is different. So you've got, in this case, instead of the vertical tubes, we've got parallel plates at an angle, which is a more conventional lamellar clarifier arrangement. And then concrete benching. So the flow comes in and is turned over, and you get settlement in this area here. The flow goes down through the dual media, the gravel pack, across to the backwash tank, and so on. So that really is the arrangement in more detail, really. And so to produce that, there would be drawings that would be sent off to the fiberglass manufacturer. They would be more detailed, focused on the arrangements of the fiberglass units. And then the rest requires a flat slab and basically plumbing together and commissioning. So there is a commissioning phase, testing and commissioning to get the system running. And so this basically, the bottom diagram here is the units they built at Cameron Sur in the Philippines, and this is basically running the test. The top one actually isn't the one. This is just really to show the parallel plates, really. That's the one for Uganda, that one. But I just now wanted to run this short video clip, which shows the backwash. This is a simulated backwash using a closed valve to simulate the clogged filter, but it does prove that the system does prime. So I hope this will work okay, and you can see this. Let me know if you can't. Is that visible?
Not yet.
So this is the inlet pipe you can see here. Sorry, this is the Apologies. This is the filter. This is the filter. That's the clarifier. That's the YouTube discharging.
Now, I'm not seeing a video running.
You're not. Is anyone seeing a video?
I think what's happened is it's popped up on another screen that you're not sharing. So you would have to unshare this and then share the one that's running.
Okay, I'll do that then. So I'll stop that share. I'm hoping now I can. Yeah, so okay, so if I go to
you should be able to find and select your screen with the video on.
Yeah, so getting now to here. Sorry about this. It's
okay.
This one, I think. Does that work?
It's not running yet, but it's try that.
You can see that, can you?
The video has come up, yes.
Okay, so just before it starts, this is the clarifier just in the very foreground. It's along the side actually. This is the filter, and that's the backwash tank, and this is the YouTube. They put a bend on the end of the YouTube. Sorry, it's not a particularly easy view to look at, but I have got other videos, but I won't go through those. But you can see now. Can you see that running?
Yes.
So if I just stop there, you could see this bit here, this very light grey shape here. That's the inlet pipe, and this small tube is in the level indication in the inlet pipe, and you can see the level has built up to somewhere near this bit of string up here to start off with. So we'll carry on playing. So that means that basically you're near to the start of the prime of the siphon. Can you see that okay, I guess?
Yes.
So yeah, you can see the initial discharge, which then stops slightly. For some reason, this does occur. There's a sort of hesitation at the beginning, as I think the air is expelled. Yeah, the water level is still at high level up here. Sorry, it's that. And then you begin to see the air being expelled from the YouTube. So that probably, I think, you can see the water level dropping in the inlet pipe now, quite rapidly. It's about here. It's quite a big flow.
Yes.
So I think I probably can pause the video at that point, actually. Because it doesn't show you anymore, it'll just carry on discharging. And that discharge actually was actually at a higher rate than the design a little bit. So we're going to have to put a valve on and throttle that slightly. And that will be part of the commissioning to get that backwash rate correct. But yeah, it proved that basically the initiation works. So that's quite a promising stage, really. So I'll go back now to my original slides. Hopefully be able to pick those back up again. Does that show?
Yes, we're back to your presentation.
That is presentation. Okay, so that's the video of the test in the Philippines, and this now is the design transferred over to Uganda, really. So this is the filter units which have been made actually in Nairobi. We identified a fiberglass manufacturer in Nairobi that we this is all done in pandemic remotely and a reasonable degree of risk, but it seems like they've come up with quite a good production of filter, at least from the photographs. It's got to be checked out, but the quality looks good. And so these basically there'll be 3 of these units operating to supply population maybe of initially 10,000 or so, I think, and then if we can supply further than that, if Edwin is on the call, he'll probably be able to say more on those figures. But yeah, so that would be to provide the hospital, which has terrible water quality at the moment, and so it will hopefully be a big improvement on that, really. The last thing I was going to just mention was disaster response. Because it's a lightweight, compact arrangement, it does lend itself, I think, anyway, to it being able to transport it in response to disaster situations. You know, if you had these available made in advance, you know, in a warehouse or whatever, you could deploy them into an area and set them up on a flat base, put in your media and your lids and commission them relatively quickly within a day or two, I would hope. And that could be a useful application for the system, really. So that's really the end of this presentation, Angus. I think over to you, really, as to where you think we go from here.
Well, I think you've kept your timing absolutely brilliant. Well done. But I don't know about everybody else, but I'm just listening to all that and just this. Who was it? Edward, I think. Edward typed quite early on, actually. He said ingenious. I just, as you described the system and how it worked, I'm just thinking, wow, that's just so clever. So they say that it takes someone very clever to make something simple. And there's a simplicity to it, using straightforward components, no power, no moving parts. And that's fantastic. So if you're happy with it, Nigel, we can go into a question and answers session.
Yeah.
And I'll say, would you like to stop sharing?
Okay.
So Scott has said, can you share what the financial cost was for the last system for the hospital for 10,000 people? That was one of my questions as well.
Yes. I thought that question might come up, actually. I think it was about for the manufacture of those units you see delivered there was I might just need to just get my file up for that, but I think it was about 800,000 Kenyan shillings.
Okay. You know what we're going to ask next, don't you?
What's the conversion?
I'll quickly do that. Okay, 800,000 you said.
Yeah, about 800,000.
1, 2, 3. So that's about £5,200.
Yeah, that's about right, I think, for that.
But
so,
the phenomenally exciting thing there, 10,000. That's 52 pence a person.
Yeah, I know. It's
52 pence a person. I just find those sort of numbers absolutely staggering, particularly when we think about what we might spend on achieving a water supply in our own country. Now, okay, you can't make a direct comparison, but 52 pence a person. That blows my mind away. Sorry,
I mean, there will be other things to incorporate as well. there's civil works, there's plumbing, and there is another tank to install, and there's any chlorine equipment and things. So yeah, there will be labour involved in commissioning, and so the overall cost will go up. You know, I think you've got to probably look at an increase. We have got costs actually for Kisika, which are more, sorry, for Kagada Hospital, which are more developed than that. So I should really, that's just the manufacture of those units, but we've got tax for import taxes, and we've got various other things that need to be added on. So really, to give a proper cost needs a little work just to extract that, really. But yeah, it is. Hopefully, it is a cheap technology, particularly if you make it in Nairobi or out there, rather than importing it from abroad. That really does make a big difference to the cost.
Yep. So we've now got a question from Alan Chadbourne. He says, where are the dimensions of 2/300 up to 600 in millimeters? Oh, where are the dimensions in millimeters?
Is that for the sizes of the filters?
I think so. I think the size of pipes and
diameters, Nigel.
The pipe diameters were in millimeters, yeah. So the 300 millimeters going up to 850 millimeters, yeah. Sorry, yeah, there are millimeters. Apologies for that, yeah. I should say actually that we did think of going to a larger pipe size than 300, but if you go to 400 or 450 with the pipe manufacturer in Kampala, Gentex, they then have to change their molding rig, which basically means it's cost them money, and you have to produce quite a lot of pipe to make it worthwhile. So, you know, you're talking hundreds of meters of pipe that you need to make it worthwhile. But whereas the 300 is readily available off the shelf. So that's really why I thought, let's stick with 300 really, the sort of background to that.
Okay. Roger has stuck his hand up. Roger, what I'll do is I'll just give you the option to unmute yourself there.
Just put it in the chat as well.
All right. Yes. Well, I'll let you read it.
So the question is, have you any experience of Moringa water purification systems?
Of what, sorry?
Moringa.
Moringa. I don't recognize that.
It's a tree that produces fruits which are used to flocculate organic matter out of water. There's quite a lot of schemes all around the tropics.
I must say I think I've heard of plant-based flocculation systems, but I've no real detailed knowledge of them.
Because the advantage, in addition to the fact that it works pretty well to get to World Health Organization cleanliness levels, you also have edible leaves from the same plant, you have edible fruits from the same plant, you have medicinal products from the plant. So the communities who are growing your material for the water purification are generating income from their farming system in parallel.
Okay. If you are able to send any details or put it in the chat.
If you Google Moringa, M-O-R-I-N-G-A.
M-O-R-I-N-G-A. Yep, got that.
Water purification. There's a lot of stuff there.
Okay, thank you. Yeah, I mean, it would be, if we can do coagulation successfully locally, then that would be a big gain. You know, it's
and the other advantage, of course, is that it's providing a farming system which is diversified and more environmentally sustainable than a slash and burn that you mentioned.
Yes. Thank you, Roger.
Okay, so now Tim is asking a question. Thank you, Tim. He says, could you tell us about the turbidity levels that it can manage? He says in the Rwenzori's area, water from mountain streams can be the color of coffee when it rains.
Yeah. Okay. Well, we have only limited data at the moment. It's very difficult, particularly with the pandemic, to have got that much data. So the only bit of data for the Mapanga Gorge one was when we went there, we used a turbidity tube, which isn't greatly accurate, but it gave us an incoming turbidity at the time we took it of about 85 NTU, and the water produced was below 5. You can't measure any lower than 5 on a turbidity tube. So that was the kind of turbidity it was handling. That probably, I would say, just based on that and the flow rate we were running, which was actually higher, much higher than I was hoping to, the filtration rate, we probably would be limited to about 100 NTU, I think, on that system. If we run it for Kaganda Hospital, we're going to run at a lot slower rate, which I think would mean you can go higher. But there is obviously, with any water treatment system, a limit. You know, anything will fall over above a certain level. You can't. So what we're thinking is that we use the dual media. The dual media does help to absorb that high turbidity load before it hits the fine media. So that's a big gain. The clarifier helps to take out a lot of the turbidity before it even hits the filter. So you've got those two benefits. But if it's a sudden torrential downpour, I've been advised that lasts not huge lengths of time. So you're talking, you know, about a day or so. We would be able to switch off the filters for a period if it need be. And just say, okay, we can't cope with that. We just got to use the treated water reservoir. We've got a big reservoir with treated water in it. So that would sustain the community for quite a while. If we need to shut off, we will, because any system will block up. So that's really where we're at. But I can't give a definitive figure for the upper limit yet.
So what would happen if you didn't shut it off?
You would actually not be able to filter enough water to provide backwash water to backwash the filter. So you basically the backwash wouldn't be sustainable, and ultimately the filter would go into a drooling mode. So the water would come in the filter and then go over the siphon and just run to waste, basically. Okay. That did happen actually at Mapanga Gorge once at one occasion.
So essentially that's fail-safe.
It's a fail-safe, yeah. It would fail, but obviously there's no water then produced for drinking water. So it did correct itself, though, after a period without any need for intervention, actually. So once the water cleared, I think enough water was gradually getting through to the backwash tank for a siphon to induce another backwash. And then thereafter, it's kept going. And for those 2 or 3 years, we've not had any interruption to the supply to the community, as far as I'm aware. So yeah, that's where it sits at the moment, really.
Tim, does that answer your question?
It does, very nicely, thank you.
And do you have any idea what the value of turbidity was on your coffee coloured water?
I didn't actually measure it, but I have seen it, literally the colour of coffee. So turbidity levels can be really, really high. You're right, I think, in that it probably peaks for only a few days, but it is a major challenge in that area. I can see from, I was trying to look on the map earlier where you are. You're some distance, I think, downstream from the Ruwenzori. So I guess that's sort of attenuated and the turbidity's probably dropped by the time it gets to you. But yes, you're right. I guess with the storage, if you've got enough treated water storage, you'd help to cover that. But then you'd have to think about the chlorination, because if it's already chlorinated, if it's sat in storage for a few days, then you've lost your chlorine and you've got no residual left.
Yeah, that's right. Yes, I mean that at our intake we do actually have some settling basins as well as a protection.
Right.
We were actually originally going to take the intake from the hydro scheme. That was the original intention, and use because the hydro scheme will have settling basins, so it doesn't foul up the turbine, etc. We were going to take the tail race of the hydro and use that to supply the water supply scheme. But because the hydro scheme is not happening as quickly as the water scheme, that delay has meant we've gone a second route now, and we've put some settling basins. But it may be ultimately that we could feed it from the hydro if that's better. It's an option.
Very good.
May I ask another question while I've got while I'm unmuted? I was intrigued by the chlorination as well. Those sort of devices with tablets and what have you can be really difficult to regulate. especially if you've got fluctuations in the flow, if it's going through at different rates and changing temperatures and things during the day. And I wondered if that is actually too simple, and whether you'd considered actually putting some sort of dosing device in there that might be easier to regulate.
Yeah, we are actually, for the Clogged Hospital, going to be putting in the dosatron pump, which is a, you may be familiar with that, Tim, I don't know which it is.
Well, I've heard of them, never actually handled one, but yeah.
Yeah, so that was basically more of a mechanical device, but uses the pressure of water to deliver the dose, which is flow proportional. And so you could adjust that, and I think that would be a much more reliable system. For the Mapanga Gorge, it is a very small scheme. It is possible to put that dosing unit on a bypass. Actually, the way it's installed actually isn't properly optimized. You put it on a bypass and you can more easily adjust the dose if you do that. The other thing is the flow is pretty bang constant, because you've got the ramp pumping all the time. So in that particular situation, it seems okay, but that's what I've heard, it's okay. But initially they did have high chlorine in the water, but I think that, as far as I'm aware, that's okay. It's difficult to get a lot of feedback, actually, because you get one-liners. You know, you said you ask for a lot of information and you just get back some very limited information. So
problem with high chlorine is it can put people off, and they can,
yeah, I know.
So
So they seem happy with it.
should we move on? Dick's asked a question. We're losing one and two people off the end now. They've got other things to go to. I'll just say that Scott says, thank you for the presentation. Have to leave now. Look forward to making this more widely known. So thank you to Scott for that. And Edward Rhodes has enjoyed the presentation. Nice to see some legacy projects of CED. I'm off now to my home group. Blessings. So Dick Waller says, what is a ZPG mixer as shown on your inlet pipe? Is it a trade name, a particular pattern, or what? I wondered that.
Yeah, it is a Zeta potential mixer, which in theory, and this I think needs testing, but it's another dried and aqua product which is designed to reproduce an element of coagulation without using chemicals. Whether or not it works, and I think we need to trial it really. But we did put it in at Mapanga Gorge, but it's basically, the idea of it is that it creates cavitation, and that cavitation strips some of the electrons from the stern layer, I think it is, on the colloids, as I understand it, and that then is taken through an earth to the ground. And that then basically creates attraction between the particles. Some become positive, some negative to a certain degree. And that was really...
That's becoming very technical. Electrons, and charges and stuff. Okay.
That's right. Yeah, I mean, that's what... But I don't know. I haven't got any real confidence in it yet, but it's something that could be tested. You could just do a bypass, try it with or without it, and just see how much effect that has. So yeah, so it's something to look at really. Can also act as a mixer, just a straight static mixer. To if you're dosing coagulant, that would mix it into the flow, as well as possibly putting in this coagulant effect.
Does anybody else have any more questions? You can either type something, or if you stick your hand up, we can unmute you. I'm suspecting we probably. I think you've given us quite a good balance of technical content, and we maybe won't go into it more unless anyone particularly wants to. But you're saying there is greater technical information there if people would like to see it, and I'm sure Nigel would be happy to share that with anybody. Out with this meeting. Yeah,
I can email those out if.
Yes, the only trouble with this is I'm not aware that I've got a means of contacting all the good people that are here tonight. So I don't have a record of point of contact. So if I wanted to, for example, if I wanted to email folks for the next Tech Talk, I don't have a means of doing that for folks like Tim there and Roger. So if you would like to get in touch, you'll find us on the CED website, which is ced.org.uk, and I'm just going to type down here. Angus at adac-structures.co.uk. Yeah, that's so. I've just pinged up my email address. So if anybody wanted to record, or if you wanted any more detail, I can do what's necessary. And if you want to be kept in touch on future talks, then I can also do that. Great. Yeah. Well, if nobody's got any other questions, I think we will wrap this up. We've been very efficient, but a lot of good information. Oh, sorry, wait. I'm seeing a hand up, Roger. So you should be able to unmute yourself, Roger, and you can ask us. Yeah.
Sounds really interesting, Nigel. I was just wondering if you'd had any conversations with any disaster response NGOs yet, because that seemed something that, you know, a system that, as you said, would be very useful in an emergency. I just wondered if you'd pursued that at all.
Yes, a little bit. It's something that I'm still waiting. We're still slightly in this is the first time we've really got those large systems made and manufactured reliably. And if we do have a source for doing that out there, yeah, I made contact with one or two contacts in the Philippines because they had this typhoon that caused a huge devastation. So I did try to contact, I think it was Care International, and there's another company I am in contact with, and they've asked for more information. But I haven't really gone much further than that, and more because I'm not exactly sure how to do that. I mean, Oxfam is another one that I do have a contact with, and I will ultimately get back in contact with them when I've got the information I can give them in a digestible form, shall we say. So the intention's there, but I haven't got that far with it yet.
Great, thank you.
One of our local friends, Ian Hall, is doing battle with sorting out his private water supply, and he's put the little note. Thanks for the presentation, Nigel. Puts our current water supply situation into perspective. Yeah. So, well, I think, Nigel, I just have to thank you very much, both for your talk tonight and for your efforts in developing and promoting the Clariwash filtration system. You know, I was very enthusiastic about the whole thing, as I said earlier. When I first heard about it, I'm just more enthusiastic now. I think you've done a tremendous thing here, and I think those of us who can need to do what they can to promote and let a wider audience know about it.
Thank you. Yeah.
Cost, simplicity, effectiveness, all of these things just been so good. Yeah, there's just another little note there. So yeah, thank you everybody who's still with us for joining us tonight. It's been absolutely great to have your presence with us. And as I said earlier, it is encouraging, very encouraging for the speaker to have an audience, and very encouraging for me and for CED to see people from outside of our group taking an interest in what we're doing. So thank you very much for being here. I'll just do a little plug for our future talks. Our next talk is well, between us, Jonathan Cox and I are trying to pull together a talk on the use of graphical information systems, GIS, and how it can be used in the developing world. That may or may not come off, and that talk may metamorphose into a talk about a project that CED did, that I was involved in at Zanzibar Cathedral. So we'll see how that goes, Jonathan. And that is on the 17th of February, and same time, same place. We have a talk in March, CED and climate change, and 21st April, sanitation in the developing world. So those are the talks that we have coming up, and we will probably wrap it up there for this year, and then run another 6 once a month for the 6 months through the winter season next year. So that's a little plug for what's coming up. So and there'll be a Facebook and an email promotion on those talks closer to the time. So thank you very much, everybody, for being here, and really enjoyed having your company and interest.